Here's something you might not have thought about. The magnetic North Pole that compasses point to near the geographic North Pole is actually the south pole of the Earth's magnetic field. That's why it attracts the north poles of magnets. But that hasn't always been true. Today's compasses would have pointed south about 1.1 million years ago, when the geomagnetic north was also a magnetic North Pole. But then the magnetic poles switched places. The magnetic South Pole went north, and the magnetic North Pole went south. They swapped again a little less than a million years ago, and again about 780,000 years ago, giving us today's orientation. Now, if you like doomsday scenarios, you might have heard that we're due for another switch that'll make electronics useless and kill us all. But that's a little extreme. And saying that we're due implies that we know a lot about when and why these swaps happen, which we really don't. The Earth's magnetic field comes from electromagnetic induction, where iron moving in the outer core generates an electric current, with the same physics that power plants use to generate electricity. And that electric current creates a magnetic field. As molten rock reaches the surface of the Earth and cools, any iron in it tends to line up with the Earth's magnetic field. So the iron in solidified lava acts like a time capsule for what Earth's magnetic field looked like when it solidified.
In a certain superhero movie, I noticed a certain superhero who used magnets to put on his high-tech weaponized suit. I was very intrigued by this and wondered how one could make magnets stronger. And not with the state-of-the-art government research facility, but at home for cheap. I finally decided a testable variable would be temperature, so I asked myself, what effect does the temperature of a magnet have on its strength? And so my Google Science Fair journey had begun. I began to research and soon found that esteemed scientist Pierre Curie had written a doctoral thesis on this very topic. I researched various sources and hypothesized that if the temperature of a magnet is increased, the magnet will become weaker. To test the magnets at various temperatures, I used a freezer, an ice bucket, and a pot of boiling water to bring the magnet to negative 15 degrees Celsius, 0 degrees Celsius, and 100 degrees Celsius, respectively. I also tested the magnet at room temperature. After bringing the magnet to the desired temperature, I tested its strength by lowering it onto a plate of paper clips. I then carefully picked up the magnet and counted how many paper clips it had picked up. My data followed the general trend I predicted. A few paper clips were lost from one temperature to the next, but in general, as the temperature increased, the magnet's strength decreased. This is because when cool, magnetic domains, or particles within the magnet that act as little magnets, move very little, so they line up and create a strong magnetic field together. When the temperature, which is the speed of the particles by definition, increases, the particles become less orderly and they don't line up as well, and the magnet becomes weaker. My final conclusion is, as the temperature of a magnet increases, its strength decreases.
While watching the compass needle carefully, we move the switch to the on position. We notice that the compass needle deflects. Again, we move the switch back to the off position. The compass needle comes back to its initial position.
You're going to see an incredible shot here. This is lightning on the ground, building, preparing to launch airborne. This is enough current to turn the magnetic molecules in molten lava to facing one direction. Here you see the lightning going airborne. After the massive amount of current flew to that spot. You'll see it here again. We will freeze it on the lightning in the ground. Most people don't see this because it happens too fast. But this is a lot of current, and this is what flows through molten lava. And this is what's responsible for aligning the metallic molecules in lava.
Let's go.